Okay. So
And
before,
maybe, since we weren't recording it, go ahead and repeat what you just said, please, so well, I get that part of the recording.
okay. Hi, my name is Kovic Suri. I'm a sixth grader at Basis Pflugerville, and I'm a so-called nerd by my classmates in astronomy and meteorology. And so today I'm going to be doing a presentation on planetary formation and the related topics. I was introduced to this in Science Olympiad, and over time it became my specialty. So before we talk about planetary formation, we need to talk about planets. A planet is an object that is naturally rounded under its own gravity, orbiting a star or the center of a galaxy. Our solar system consists of 8 current planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. There used to be the dwarf planet Pluto, but in 2006, the International Astronomical Union introduced a criterion to become a planet. Pluto did not meet the third criteria to clear its orbital neighborhood, and so it's a dwarf planet. So why should we study planetary formation? There are several reasons. It can give us insight into understanding Earth's earliest history and how our solar system and how life may have even formed. Theories like the nebular hypothesis and the NICE model attempt to explain how the system formed and how the planets got in their current places. Second, it helps us understand other planetary systems that have planets in different stages. So we could use those to compare with our planets and find out certain questions like why is Mercury a small solid rock while Jupiter is a giant gaseous planet? Third, we want to find planets that could be habitable. This relates to the age-old question, is there life outside of our solar system? Or maybe in our solar system too? Studying planetary formation helps us find what could happen, what may happen, and what already happened to see if life exists. And the last reason is humans are, well, naturally curious organisms, and we want to know what's coming in the future so we can study planetary formation. Okay, let me give an example. Say there's a super Earth, a exoplanet that's like sort of like an Earth, almost the same to an Earth, and then it's older than Earth as well. So we could use that data to find out what could happen to Earth in the future. There's a thing already that explains, well, attempts to explain that called the Milankovitch cycles, but that's getting into meteorology, and I'm not gonna talk on that today. Okay. So these are the popular theories on planetary formation that I'm going to be talking about, which are the nebular hypothesis, core accretion theory, and disk instability theory. First of all, before we get to the theories, we need to understand molecular clouds. Molecular clouds are massive clouds of gas and dust floating in space, sometimes even like more than hundreds of light years across. And the key thing about molecular clouds is that they are extremely dense. And once a region of that cloud gets extremely dense, like dense enough, it triggers gravitational collapse because of its own mass. It's too heavy, so it just gravitationally collapses into a protostar. Now, this is like how every star system forms, and it's also, I guess, part of a theory, the nebula hypothesis theory. So the protostar, it has a massive gravitational pull as well, and this pull turns the dust around it the gas and dust around it into a spinning disk called the protoplanetary disk. And eventually planets will form, but we'll get to that later. Okay, so the nebular hypothesis theory, the first and most widely accepted theory of planetary formation, it was developed by Immanuel Kant in 1794 and then modified by Pierre Laplace in 1796. So the molecular cloud we just talked about, the nebular hypothesis is sort of like an add-on or a continuation of that. It picks up right where the molecular cloud leaves off with the spinning gas and dust disk. And so we know the protostar and all that. As the cloud collapses, it spins faster and faster due to something called the conservation of angular momentum. And the gas and dust in that disk bumps into each other to form a thin, flat plane, all orbiting in the same direction around the protostar. So the spinning collapse forms the material to fall into the star, into the protostar, gradually adding more and more material until it becomes a full-on star. So over time, and the star, it captures even more gas and dust to replace the one that it lost. So over time, tiny dust grains in the disk, like tiny, extremely tiny, the smaller than the width of a human hair. You can't even see them at that point. But they start bumping into each other, and due to something called electrostatic forces, stick together. Now, as they stick together even more and more and more, slowly form pebbles, rocks, then boulders, until they form what's called a planetes, a small body that's at least 1 kilometer in diameter. So, uh, the nebula hypothesis explains a lot of the things that we observe today. Why planets orbit in a flat plane. I mean, there's some exceptions, and why planets all orbit in the same motion around around their star. Now they can be in like different motions, retrograde motion with Venus. Uranus is tilted like this from the plane. A lot of other exceptions, but it explains most everything. Nebula hypothesis doesn't explain everything though. It doesn't explain hot Jupiters, which is a exoplanet type that's Jupiter sized, or most of the times it's bigger than Jupiter, that orbits extremely close to its star, sometimes even within the orbit of Mercury. It also doesn't explain Mercury's retrograde motion. So like the point is not all theories can explain everything. There's also a famous problem in astrophysics, which is called the angular momentum problem. The sun holds 99% of the solar system's mass. That's like so much that you could just call our system the sun with just a bunch of tiny debris. The It holds 99% of the mass, but only 2% of the angular momentum, the spin. If everything came from a spinning molecular cloud, then you would expect the sun to be going much faster than 2%. This is still a major problem in astrophysics.
I think it's because I have it on and I'm trying to turn it off.
I will just mute everybody from here.
I'm sorry.
Hold on, I'm sorry.
Still play on her phone.
No, I'll mute her phone.
Right,
Oh, yeah.
right.
Okay, yeah. Okay.
My phone has that problem too.
Go ahead.
Okay,
Sorry, go ahead.
it's fine. So next we're talking about proplids, which is short for protoplanetary disks, the swirling thing around the stars. These are the actual disks that the nebula hypothesis predicted would exist. We can see them only with powerful telescopes because like normal space telescopes, they're they just capture the nebula or the molecular cloud which they're in. They don't capture the actual disk. So the first problids were discovered by the Hubble Space Telescope in 1992, and it was in the Orion Nebula, and it was pretty detailed actually for a picture taken in 1992. And there's another really famous photo by
Just
ALMA,
turn
which
the
is
show
the
up. I'm
Atacama
so
Large
interested in what's.
Submillimeter and Millimeter Array.
Yeah, here, let's just turn the phone. I'll just.
It took a famous picture of the star HL Tauri, and that that like revolutionized astronomy because HL Tauri is very young in astronomical years in astronomy terms, only like a few million years old. And so the ALMA detected rings and gaps in the problid of HL Tauri, which indicate forming planets. This revolutionized astronomy because HL Tauri, well, it proved that planets can form in stars much faster than previously thought. Okay, so the next theory is core accretion. This is another popular accepted theory of planetary formation and another continuation or add-on to the nebula hypothesis. I mean, it's basically just the nebula hypothesis continued in more detailed, but created in 1944 by Otto Schmidt and developed in 1969 by Viktor Safronov. Core accretion focuses on how planets actually grow within the disk, not just the molecular cloud collapse and the protosun, the protostar. It starts with what I said earlier, micron-sized dust pebbles, and then slowly goes to boulders, and keeps going until it forms a planetesimal. Now, this is where nebular hypothesis leaves off at planetesimals. So after planetesimals, they keep growing and growing and growing until they form protoplanets. Now, there's two sections to the protoplanet formation, inside the frost line and outside the frost line. Now, I'm going to get to the frost line in a minute after this slide, but it's the distance from the sun where it's so cold that water can exist as solid ice. And so inside the frost line, there's not much material to grow because the protoplanets already took most of the material. So there's not much material to grow larger. And so with that, they just stop formation, I guess. Sort of like that. They keep gradually growing and growing, but they stop formation with a mostly thin or no atmosphere and almost no a magnetic field or almost no magnetic field. That's why we have small terrestrial planets like Venus, Earth, Mars, like that. Now, outside the frost line, it's so cold that water can exist as solid ice. Now, since there's more solid material, it adds like 2/3 more stuff to accrete, to grow onto. And so planets there, protoplanets and planetesimals, can grow much, much faster and much larger than inside the frost line. So this leads to the protoplanets starting runaway gas accretion, where it constantly adds on gas to itself until it has like almost fully gas layers and a thick atmosphere.
Good Irish names.
It can also do this because while the system is spinning, most of the gas gets transferred to the outer layers, and the planets there can accrete more too. So I just talked about the frost line a lot, but in detail, the frost line, also called the snow line, is the boundary, or well, there's not like a physical boundary, but it's the distance from the sun where the temperature is the temperature is low enough for water and other volatile elements like phosphorus or nitrogen to freeze into solid ice. Inside the frost line, it's too hot So water exists as water vapor unless you're in the Goldilocks zone or habitable zone where water can exist as a liquid. Not like solid though. So solid ice means more material to build on. The planets can grow faster, grow larger, which I just explained all that. This is why planets inside the frost line are small, rocky terrestrial planets. There just wasn't enough material to grow large like Jupiter. Okay, so now let's talk about our planetary system's formation, or the solar system's formation. So it started from a molecular cloud just like any other system about 4.6 billion years ago. Scientists think a nearby supernova explosion triggered the collapse of the molecular cloud, and the shockwave sort of kick-started the protosun. Following the nebular hypothesis, the cloud collapsed and the protoplanetary disk, formed. The whole core accretion model went through. Sorry. The whole core accretion model went through inside and outside frost lines and all that. And so beyond the frost line, Jupiter and Saturn formed. Was actually the first to form in the solar system, and it pulled in a lot of the gas and dust before any of the other planets could. Saturn formed shortly after and also pulled in a lot of gas and dust. So, but it didn't get quite as large. So Uranus and Neptune, though, they formed much further out, like really, really far away from the sun, and created some like an okay-ish amount of material, not enough to become as large as Jupiter or Saturn, but at least much bigger than Earth. So they back there, the temperature was so cold that um like they were almost completely frozen over. Like even inside Jupiter, I'm sorry, Uranus and Neptune, outside their rocky core, you can, well, it's not actually a rocky core either. It's an icy slash rocky core, but the rest of it is just ice, then a layer of methane and ammonia. So next is after the planets formed is the NICE model. This we'll discuss it in the migration slides coming up, but it just explains how the planets moved from their places, migrated, and how the planetary system was formed. So these migrations had huge effects because, according to the Grand Tack hypothesis, Jupiter orbited inwards towards the asteroid belt and completely scattered all of it. Like some of the material was ejected so far out that in kilometers, it's like way too big of a number to say. And then the rest of what remained of the asteroid belt, 50% of it was ejected, by the way. The rest of what remained in the asteroid belt formed the ring that we see today. And even now, the ring is incredibly dense. Back then, before Jupiter migrated inwards, it was 2 times denser and more massive. And it was getting close to starting to become a planet too. So we could have had a fifth terrestrial planet if Jupiter did not migrate inward. Jupiter also scattered the gas and dust around the area of Mars, which prevented Mars from becoming larger and getting an atmosphere. I mean, Mars did have an atmosphere, but it was blown away by the sun, so it would have had an even thicker atmosphere. It took about 100 million years for the planets to come into the positions that we see them today after they were formed. Okay, so the next model is disk instability. This is another not as widely accepted as nebular hypothesis, but it's still a famous one up there. Um, so this is like after the nebular hypothesis. So in some regions of the disk, it can become so heavy and dense that it just gravitationally collapses straight into a gas giant. It doesn't need a core, no outer layers. It just like compresses and then explodes into a gas giant. Now it's not instantaneous, not in like minutes or seconds. It takes thousands of years, but it's still the fastest planetary formation method. So when would disk instability happen instead of core accretion? Scientists are still debating on that, but um, the common answer is that if you have a extremely cold, extremely massive, and extremely dense disk, because disk instability it doesn't explain like terrestrial planets or the frost line. It just explains cold, massive, far out gas giants. So like they have to be so far from their star that possibly like in the orbit of Pluto-ish, Neptune to Pluto maybe. So there's a debate among scientists about how common disk instability really is. A lot of scientists think core accretion is the best theory and most accepted, while others think disk instability is more likely, but it depends on the protoplanetary disk and the conditions of it. We're still studying to figure out which one is better. Okay, so now we're on planetary migration. Planetary migration is when an object moves through a system through a long period of time. It doesn't happen like fast. It's not like walking, but it takes a really long time, sometimes millions to tens of millions years. So migration happens when planets interact with the protoplanetary disk. The disk of gas and dust has a gravitational pull too, not just the planets. And so that gravitational pull also pulls the planet with it, and it can orbit in or outward. There's two main types though, type 1 and type 2, and planetary migration shows that planets don't stay where they form. It is extremely rare for a planet for its current position to be where it formed. So this is the like most likely for every system. Okay. So type 1 and type 2 migration. Type 1 migration is with low mass planets, Earth to Neptune size. The planet has to be embedded inside the gas disk and usually migrates inward towards the star. This is a pretty fast process, can happen in about 100,000 years. Now, type 2 migration is a bit rarer. With high mass planets, Jupiter-sized or larger, though it's extremely rare for this to happen. So the planet opens a gap in the disk and just cuts through it slowly. It's slower than type 1 and can migrate inward or outward. So how does migration shape the planetary systems? Well, it happens during the planetary formation, not after. That means migration and planetary formation are deeply connected. You can't have one without the other. Now, migration determines the final architecture and structure of a planetary system, where planets end up and how they're arranged. Hot Jupiters are the perfect example. These are gas giants that orbit extremely close to their stars. They're about Jupiter sized. Sometimes even like they orbit even within the Mercury's orbit, which is quite mind baffling if you think about it, because Mercury is 0.0 0.02 AU from the sun. These are even closer. So hot Jupiters, they didn't just form where they are. They've based on like their mass, which is about like usually 4 to 5 times the mass of Jupiter, which is also insane. They formed very far from their stars, then due to type 2 migration, cut through their disk and made their way to the center, well, not center, center of their system. Migration can also create resonant chains or orbital resonances. This is when planets get locked into ratios, like in their orbits, like Neptune and Pluto's 3-2 orbital resonance, or the Laplace resonance of 1 to 2 to 4 in the Galilean moons of Jupiter. Migration helped shepherd and move these into their precise arrangements. So in the solar system, as I talked about before, there's the grand tack hypothesis, as I explained, like how Jupiter moved inward, then outward. It actually started like right here, then moved here, then now this is its current position. The same thing happened with Saturn, actually. Saturn was the only thing pulling back Jupiter from going further. If it went further, then it would have disturbed the orbit of Earth too and prevented it from accreting more, and it could have prevented life on Earth too. So Saturn was the only thing stopping Jupiter. It's Saturn's gravitational pull was the only thing stopping Jupiter from disrupting Earth's orbit and going even further. I mean, Jupiter, for all we know, it could have become a hot Jupiter because at the speed it was migrating, because it was just destroying everything in its path, just disrupting everything. Saturn basically just saved the solar system. I mean, you could put it that way.
Yay, Saturn.
Yeah. So thank you so much for letting me present here. I really appreciate it, and it was really fun. This is an ongoing topic that's still being studied a lot, and there's many theories I haven't talked about, like tidal formation or pebble accretion. Most of them are theories, well, we don't know about them at all. Hopefully, we gain new knowledge by like the month, and hopefully there's gonna be new stuff to learn, and maybe I can even present this again. Thank you.
Very, very nice. Thank you so much. Anybody got any questions real quick?
Yeah.
Yeah, go ahead.
Go ahead.
So you talk about the frost line, and inside of the frost line, the polar zone and the outside, right?
Yeah.
So that kind of explains the inner planets.
Yeah.
If they have, and then it also explains the ice giants. But
Yeah, the ice giants.
Jupiter and Saturn, which are outside of the frost line, but still don't have.
Back there, it's cold enough to have more material. Like, I mean, if you look inside their cores, there's some ice. Jupiter's clouds and Jupiter and Saturn's clouds contain ice. But back there, it's not cold enough to have their cores freeze into solid ice. It's cold enough for water to exist as ice and accrete more and more material. But it's not cold enough for the cores to freeze over and become an ice giant. Okay, anyone else go ahead.
Yeah, I was wondering if these hypotheses that you described, if they all predate your modeling, or maybe like some of them might have been augmented as computers.
Hey, you're not at your.
Yeah, that's the thing though.
Well,
Some
that's it,
like
right.
nebular hypothesis and core accretion,
Well,
they were
stands,
actually proved by
Huh?
computers. Nebular hypothesis was created back in 1794,
That's okay.
but current computer models
Yeah,
still
I'll
show
be
that
Yeah.
that is partially true and still widely accepted. So it's the same with core accretion. Okay, anyone else got questions?
Any questions?
Are these theories exclusive?
Hey, well, let's
All right.
wrap it up.
You talked about
Thank you.
core accretion being
Oh, yeah.
added on to
Oh, yeah,
the
there's-
planetary
Oh
nebula.
my God, there's
Questions on the chat.
18.
No,
Yeah,
no, I'm monitoring.
you are monitoring. Okay, no questions. What are the 18 chat messages for?
The echo.
Oh, the echo, okay, yeah. Yeah, and we need to, Jim, let me let you take this back. And did you get your drive?
That's it.
That's it, okay.
That's
We'll deal with it
COVID's
later.
drive.
Okay.
Jamie,
Um,
Jamie,
so, what we need to do is mute everyone. And we're gonna do our visiting.
Uh,
can anyone hear the audio from the Zoom?
Yeah, give me a minute.
Hang on, guys, we're getting everything.
We can hear it from home.
It got disconnected, hang on.
You could stop sharing.
Yes, I hear it.
He's gonna get to that next. Give it a minute. Okay. Let's make sure this is gonna connect first.
Should be coming back.
The actual connection to the room stuff got when we were moving it. There we go. Okay. And then if you can, actually, he's sharing the whole screen. There you go. Yeah, perfect. Got it. Okay, and then is everybody muted? Let's go ahead and mute everyone except that'll be up at the top, the very top. Is there anybody who's not muted? I know there was some comment online that some folks were not muted. Yeah, you can actually kill this whole thing. And do you see that anyone's not muted, Rajesh?
Yeah, there are some people who want to ask questions. but
Okay.
We want to give them an opportunity before we start this.
You can click that little X, and get out of this. Okay. Yeah,
Some
gotcha.
people who want to ask questions, you want to give them an opportunity, or you want to hold on to that, finish this.
Okay, well,
Yeah.
yeah, we need to get the business meeting started. Yeah, if we can do that afterwards.
Yeah.
That'd be great. Sorry, our normal person who does the Zoom is not here. And so Jim is filling in, thank you. And so, and also we're in a new room, so we're just figuring out the connections and everything. So thank you so much, COVID, and thanks for your patience while we have interruptions and fun things. Very nice. And so let's go through the business meeting really quick. I think most of the folks are not here, but Joyce is here. So do you have a report from? Well, can't hear you as well over there. So yeah, sorry. That's all right. And should we be in front of that, or what do you think? Yeah, I'm hesitant to move it because.
Whatever. Everybody knows what I look
Who can see?
I'll get it, Jamie.
No, I'm not, I'm just wanting to see who,
Oh,
what the camera is looking at. Of course, we're sharing, so I guess the camera isn't gonna show.
Yeah, we are just showing.
Okay. So we're using the laptop camera, not this camera
yeah,
right here.
let me,
See if we can get it.
no,
So you can see everybody in the room, yay.
Where's the camera?
what I'm trying to see. Let me bring this down where I can see the whole screen.
Well, while you're messing with that, everybody can hear Joyce?
I'll just go ahead and hook it.
Can you guys hear her okay?
Yes.
And they can see her now.
There I am.
Okay.
Okay, well, I thank everybody for your patience with coming to a different room tonight. We were kind of at the mercy of UT in terms of what rooms are available, but this room is just fine, and I hope everybody managed to find it. Next month, we will be back in our usual room in ETC. For July, we could not get a room on our normal meeting night, so we are going to go to St. Stephen's Episcopal School to Frank Micah's classroom and his observatory. So that will be that's always a treat to go out there and do that in July. And then August, we're at a different room across the street. I'll let everybody know. And but then hopefully back in the fall, we'll be back in a regular room. So that's kind of an idea of what's coming up. Thank you.
Awesome. Thank you, Joyce. And then, we can go back to here we go. That's handy, having sharing the whole screen and then you just click on different things. So, we have Charles would be next, our treasurer, and he did send out an email with his treasurer report. And it is going to be in the newsletter too, I believe. And that should be coming out any day now. And, you guys can see that, but I don't have. I didn't think to get his report to show folks. Oh, okay. And I've been getting messages too the whole time from different folks. So, okay, that's good. All right. And then everything basically though with the treasurer report, we're still in the black. So yay, everything's going well. And then for the communications, is Sean online for the communications position? Does he happen to be on Zoom? I think you can unmute yourself if you're here.
No, I don't think so.
He's not, okay. Yeah, it's kind of tricky this month because a lot of folks are busy getting ready for the Texas Star Party, so they are not here. Including our person who usually does runs the Zoom meeting, all that. So, okay, so for Sean, basically what's going on is that we're having some trouble with our email lists. And he's been setting up lists, for example, the EC list, so that we can send an email to that and get everybody who's on the EC. And there's some filtering problems with Gmail and Google, and so not everybody's getting everything. And so he's proposing setting up groups. And we did look at this on Monday, and looks like we're gonna go with setting up Google groups. I don't know exactly what that means, but that's what's happening. So just to let y'all know.
It's already set up.
It is set up?
It is set up and then we've tested it. I think that should be fine.
Okay, perfect. All right, thank you. And then our next position is our equipment chair, who is now is Greg. It was Ernie, but Greg has taken over. Thank you.
Yeah.
For the rest of this term, which is the end of this month. And then he's going to continue on. So thank you further. But do you have a report to tell us anything about what's going on with?
Well, let's see, we had telescope workshop on the 4th, I believe it was. We'll have, the next one will be
Last
on,
weekend?
yeah, last weekend.
Yes.
The next one will be on the 30th of this month. And we will be doing an open house again at area 51.2 for that. So we'll have drinks and pizza or something like that, I think.
Yes. Yes.
Ernie and I are working on a system for creating serial numbers for all of our scopes. So we can have like actual identification numbers on them instead of just vague descriptions.
Nice.
And we're taking photos of all of them so that we can eventually build a web page that shows their status, whether they're checked out or checked in, you know, so anyone can get on our webpage and see what's available.
Wow. Wow, that's even better. I love it. Yeah, so we do have a lot of equipment and we loan telescopes and equipment out, and it's a great program. And then for some workshops, and then I'm sorry, I was looking at another report. Did you say about the open house?
Yes,
Oh,
yeah. The open house will be on May 30th.
yeah, that we had one a few last year, and people would just come and go all day long, and we do have pizza, and it was a pretty good event. We had different telescopes set up. You were doing a demonstration of cleaning mirrors, and there was a lot of fun stuff. So very cool, and centrally located at our East Boston storage facility.
Does everybody know where area 51.2 is?
Freedom. In the warehouse district, East Austin.
It's disguised as a business on East Fifth Street called White Mountain Foods.
Yep. It's in the same building as that. Oh, very cool. So awesome. Thanks, Greg. And you're working on the wiring to get our trailer.
The trailer wiring is done.
Really?
Yes,
What? Damn, that was just Monday we were talking about it. You already got it.
it's done.
I'm impressed. Okay.
The new flow is better.
What's that?
The new crew is better.
The new crew, yeah. Well, very nice. So we have this trailer that we bought fairly recently.
Yeah.
That already Greg has been taking to different star parties, different public events. And carrying one of our big telescopes, the 25 inch,
24 inch.
24 inch. Oh, okay, well, that's the small. I'm kidding.
The
It's
spike
huge.
eye.
The spike eyes. It's huge, it's awesome, and I was at a star party event where you brought that and.
Yep.
And it was a big
And-
hit.
And in fact, the trailer and Spike are going to Texas Star Party.
Oh, really?
Yes.
So,
That's
well,
kind of
interesting. So what about us folks who are stuck here in Austin who want to look through it?
It'll be back before the next Star Party.
That's just gonna be
tomorrow.
Huh?
Next Star Party is tomorrow, isn't it?
tomorrow night, yeah, Ferdinand Falls, I think,
Oh,
right?
is it?
That, yes.
Yes,
Okay, well, I lied.
Weather is.
yeah, the weather is.
Yeah, yeah. Well, it's maybe Sunday morning for TSP.
Okay, okay, good, so we do get it for tomorrow, that's awesome.
Yeah.
Very good, thank you, Greg, thanks for stepping in and for all the work. And then who's next? Member Services, Terry, where's Terry? Where is that man? He is, actually, he's already in West Texas. He's staying with a couple of former members of the club, the Chandlers.
Yeah.
Yeah, and so he was telling me, yeah, I'm going 2 days early to observe with Jim and Anna Chandler and out in West Texas, so must be nice. So that's where he's at, so no report for member services. And then our outreach main person who's doing all the work isn't here, but Joyce is our interim outreach chair. That's kind of a funky situation. But do you have a report for outreach?
I will just say that as we have just been discussing, there is a star party scheduled for tomorrow night at Pedernales Falls, and looking at the clear sky clock this afternoon, it looks like it's gonna clear up by tomorrow evening pretty well, so I assume it will be going forward.
Cool. Okay, very nice. And one thing, we just had our executive committee meeting on Monday. And that's this group of folks, we get together and, make sure everything's running and public star parties happen and all that kind of stuff. And as I mentioned at our Monday meeting, which is open to anybody, if anybody is interested, to want to come and listen to how the business stuff behind the scenes works. The Ferdinand Falls State Park is where we have our kind of a permanent facility. We've got a Connex building out there, Connex. What do you call those things? Shipping container?
Yeah.
Yeah.
It's a shipping container.
It's been turned into our observatory, Falling Star Observatory, and we do have a lot of telescopes out there, including that 24 inch spike eyes, and there's a 25 inch out there.
Yes, that's the Larry Forest, which is also at in West Texas.
Oh, is it really?
Yeah, Terry took that one.
Damn, did you guys ask the EC, can we take these telescopes?
We had a secret vote. We didn't tell you about
I
it.
guess, I mean, seriously, this is something people have to pay for to go to, and wow, okay, I don't know about that.
Well, I mean, we have to test out the telescopes under actual dark skies. I mean,
Right,
Pedernales is only like a portal 4.
yeah,
Okay, that's not sufficient for accurate testing.
yeah, that's a very interesting, event, I'll have to check into that some more.
So we consider it to be starlight maintenance.
Yeah,
Okay.
yeah. Interesting. Okay, so anyway, I wanted to mention that Ferdinand Falls also last week participated in the Great Texas Birding Classic. They got rained out, but the name of their entry, their group, it's a bunch of different groups that compete. And their group is called Ferdinand Falls State Park. So I just wanted to mention that to people because folks sometimes want to pronounce it the way it's actually spelled, Pedernales, and even that is not correct. I'm supposed to roll the R and I can't. But if you're a native Texan and it's always been called Pedernales Falls, yes, exactly. So that's the proof right there, is that they called it Pedernales. They called their group Pedernales. So yeah, I love it. Just wanted a little point of contention there, but a little controversy, fun. Okay, and then our next report. The member services position, by the way, is one of the ones that is still open. And that he does things like schedule members only star parties and other events that are a benefit to our membership. When you do become a member of AAS, there's a lot of perks, of course, that come with that. So he manages a lot of those. I'm sorry, and then outreach, we got that, and then members at large is Brian is not here. He's guess where. Yes, actually, I think he might be
No, he's
online.
on Zoom.
Is he on Zoom?
Yeah.
Okay. Hey, Brian.
He's right here.
And then
Can
I
you hear
think
me?
Bill. And then Greg was member at large, but now you've moved on to the equipment position. So basically, do we have any reports from anyone in the member at large position?
None that I'm aware of, other than pictures from TSP at some point.
The new term.
It says talking Brian Lippincott, but we're not hearing him.
Brian, are you muted?
No worries.
No, guys, they can come online, we can, no.
Oh, okay. That's unfortunate.
It says nothing to report.
Okay, thanks, Nielsen. All right, good thing because we can't hear you. I'm not sure why. All right. And then our social media coordinator, Anshu, I don't think he's online.
It's exam week, so he's not there today, he computed me, So from all the social media channels that we have, the most engagement happens in Insta. So
In what?
In Instagram.
Instagram? Okay.
Yeah. So the only request that he has is that members send across pictures from events that are being held, as well as astrophotography pictures, whatever you have. Because the more content we have, the more engagement we can form. So the request is for you all to send more images that you have to be awesome.
Content, give us content. Very nice, thank you. That's Anshu Dad right there. Okay, and then dark sky coordinator who is also rolling off, and I see that you are here, Susie. Hey,
I'm here.
yeah,
I'll come down here. It's kind of dark back here.
yeah,
Yeah.
and this is where the camera is. Someone else stand in
Yeah,
front of it.
we can see Greg okay, so I'll just stand next to Greg.
Yeah.
Yeah. So, yeah, handing this off to Jamie. And I just want to say to the club at large, this whole fight to reduce light pollution, it's an uphill fight. It's gonna be rough with developers and Buc-ee's and the rise in everything that, advertising is lighting. And so I really encourage everybody in the club to have a real role in this by either getting active with Dark Sky Texas or Dark Sky International. So we just went out to West Texas for Dark Sky International's week-long activities out there. And every community out there, of course, Big Bend National, it's actually Big Bend Dark Sky Preserve, which is much bigger than Big Bend National Park. It's the largest dark sky preserve in the world. And that for them to be able to save that and keep it is going to require a lot of work from Texans. Because, the first thing is the wall, they want to build that and light it. But there's just going to be constant, efforts of people to put up lighting out there and to keep that and to keep Fort Davis, where a lot of our members are right now, as Portal 2 instead of, Portal 4 like Pedernales Falls. It's just going to take a lot of activity, and you can give them some money, you can get on their newsletter, you can sign up to help, you can invite speakers to come. And I know even at our own HOA, just standing up and saying, I have some handouts. I have lots of handouts. I printed a bunch of them. And so if anybody ever needs those for a star party or for a neighborhood event, just to spread the word in your own neighborhood that, the 5 principles of good lighting. It's very simple and it will really help. And once people hear about it, they're like, I'm interested in that. I want that. And of course, it increases your property values to have that. It's something like tripled in 10 years on astrotourism. So it's really valuable that we all get behind that. And everything else I have is in the newsletter, but especially all the stuff about West Texas, which was great fun, all the star parties. So good luck, Jamie. I think it'll be a great effort for us to continue.
I'm supposed to be moving into her role, so, yeah, we'll see. That's assuming that I don't have to be present anymore. Thank you, Susie. Okay, and then, I got an email, by the way, from Anju, said he is overloaded right now and won't be able to make it, but he'll be here next month. And still is continuing his work. Okay, and then we've got our Alcor representative, which I continue the acronym, I keep spelling it wrong, it's supposed to be capital L. But that's Astronomical League, which is sort of the overseeing organization that all of the different astronomy societies are members of. And as members, each of you, as members of the club, gets a quarterly publication from the Astronomical League called Reflector. And they also have a whole bunch of observing programs. And I do have a report from Joy. Is she on actually? She's not, okay. I got a report from her that she is also submitting to the newsletter. All of our reports also go into the newsletter. But here's the report and it's long. So I'm not gonna read it to you, I mean, unless you really want. It basically, it's about some of the observing programs that are available. Those are really cool to sort of help you focus and get involved in a particular set of observations you can make and keep track of, and then you get cool things. Like I got it. Yeah, absolutely. And there's also, they did have a webinar May 1st. And it's available on the Astronomical League website if you're interested. They featured a woman, astronomer, is she amateur astronomer? I don't know, Prandera Hysenide, who is from Kosovo, and she's famous. A lot of people here know her, I don't. But she had a good talk, and then there's just a lot of observing programs. So good stuff. And what's next after Joy? Oh, okay, just the business. And Rajesh just reminded me, I've been doing this as president for 2 years and then vice president before that for 2 years. And I still forget to say at the beginning of the meeting, hey, do we have any visitors or new members that would like to introduce themselves? So
that's why we are letting you continue for more time.
What's that?
That's why we are letting you continue for more time.
Yeah, oh, after this, yeah, so I get it right.
And you're right, yeah.
Yep, got it. So, yeah, go ahead, there's a.
I'm not a new member, but this is the day, it's like the 40th anniversary of me being a member.
Oh, yeah.
My name's Ellie and I'm visiting from South Dakota.
Wow.
I've been in town all week for a work conference and I'm an amateur astronomer. I Googled astronomy in Austin and found this, and so I showed up tonight. So thank you for having me.
Where did you see this from?
I found your website.
Oh.
Yeah, or Google search, hey, it works, nice,
It
well,
does.
welcome. Any other new folks that wanna embarrass yourselves, go ahead.
So I'm Al Winchester. I'm a senior from Austin. I'm an Austin native, but I'm actually going to UT next year, so I will be here for the next 4 years.
Nice.
Congratulations. Thank you. At my high school, I was the president of my astronomy club. I have to say, I'm not very acquainted with it though, because you didn't really have a lot of support, unfortunately. But I'm glad to be here. So yeah, I've been wanting to get involved for a while, but I've just never like acted on his losses of pretty reversible. But now I'm here, so yeah.
Very nice, we're glad to hear.
High school.
Lost liberal arts and science. Liberal arts and science.
Oh, yeah, we did we did a star party for your group, yeah.
Oh, nice.
Nowhere else.
Yep.
Any other new folks? Yeah, oh, there's somebody, yeah.
We're Hannah and Chris, and we're just here to check out everything. Awesome. Well,
Very good.
like,
Very glad you're here. And then, anybody online? Do we have new members or visitors online who would like to say hello? I mean, I don't know, maybe we can't have you say hello, because for some reason. Can you check the chat, see if there's anybody? No, okay. Boy, there's a lot of comments. There's 31 comments on there.
So mostly me.
Yeah, okay. Yep. Very verbose. Very cool. So glad everybody's here. And then I'll mention for business, oh, it's 8 o'clock. So wrap it up quickly, but we still need 3 people. We had a wonderful nominating committee. Nielsa back there was part of it, and Cindy Nance, I know, was online, and then Rajesh. You guys were great. Thank you for trying to round up people. It's an interesting situation, and I guess this happens with a lot of clubs, volunteer clubs and groups, where we have nearly 500 members, and we cannot get just that roster filled up from 500 members. What? So we still don't have, the term ends this month. It's the new term, 26-27 term starts in June. And so we do not have a vice president or a president or a member services chair. Now, we do have Terry, who's floating. He's waiting to see what happens, and he's gonna land on one of those. But there's a little hesitation just because I think he doesn't want to be president or vice president and get saddled with both positions. But the problem is that Joyce and I both are limited by, the bylaws have a term limit for president and vice president. Not for any of the other positions, but for us. So 2 years is the term limit. And we were thinking about, again, switching, because we did it before, 2 years before me, you were president. But we're both kind of like, get somebody else, please take this one. It's not that hard, and it's perfect for somebody who's retired and has a wife and somebody at home, to help take care of things. Yeah. But you're managing on your own there, right?
So one comment,
Yes.
Brian says that Panvera is a professional astronomer specializes in astrophysics.
That what, say that again?
Panvera is a professional astronomer and specializes in astrophysics.
She is professional. Okay, very cool. Yeah, Greg missed my comment, so I just volunteered you for a position. I hope you're okay with it.
Just say that again.
Yeah. Yep. Okay, and then the other thing, just wanted to mention the open house. So we're pretty much done, and I want to mention this young man who's coming to UT, and we're excited to be at UT. Kyle is a research professional here, and I want to be him when I grow up. But today I found out I finally got from an incomplete class. I had come back to school here for a couple of years, and I finally got my grade for my probability and statistics course that's been dogging me. And I've been working on, it's a B+. I'll take it. I'm so happy. And I've been working on this paper where folks have been using probability and statistics to image the black hole at the center of our universe, and also at M87, if you're familiar with that. And there's a lot of like predicting, what are we going to see? What do we expect to see? It's an interesting way of imaging things. And my paper talks about, does that limit what we do see, or color what we see? But anyway, I'm done. I just have to send in a couple last chapters, but she submitted the grade today. And so, I'm done. Yay. I'm excited about that. All right, I guess we're, go ahead, Joyce, you want to introduce the?
Okay, I'm concerned, are we not hearing people?
Oh,
on Zoom?
that could be a problem if our speaker's on Zoom, isn't it?
Yeah.
Yeah.
The test we did at the start of the meeting, we could hear people.
Right, but we couldn't hear Brian.
Right, well, what is it, James?
Don't forget Brian's out where there's like hardly any service at all. Out in Fort Davis.
I don't think he's already out there.
Oh, okay.
No, he's at home.
Yeah. Well,
Testing.
Well,
Testing.
let's make sure, is Rob Zellum here? Is he on Zoom?
Hey, can you hear me okay?
Okay, he is talking.
I am talking.
Yes, I'm logged into the Zoom on my phone.
Oh.
Turned it up high enough that other people heard me, but.
Okay, yeah, if you can kill that. Rob, are you there?
I am here.
I think we can still not hear them. Not a lot of people can hear. They will come off when we move the laptop.
Okay. Did it get disconnected? Because we are not hearing room speakers.
No, if it was disconnected, we'd have no video.
Right. So we were able to hear room speakers at the beginning.
Can you hear me now? Hello?
We can hear you on Zoom, Rob. That's all that really matters, right?
Perfect.
Yes, I can hear you. I can hear you. This is Rusty. I can hear you.
It has really been a group effort this evening, so,
So is the sound coming through the HDMI or through something else?
It's supposedly coming through the HDMI.
Yeah, it should be coming through the HDMI along with the video.
This is on. I'm muted.
Yeah, so 1 second.
Volume's up maximum.
Can somebody try speaking? No?
Hello? Can you hear me now?
It's the volume on here saying.
Oh, it's off.
Yes, I can hear you.
Yeah. There we go.
Can you hear me now?
Yes.
yes.
Yay.
I want to introduce you. Where should I stand? Please, everybody.
Yeah, go ahead, Jim. Where you want to put it.
Do I see it on your PC?
Yeah, we'll need to fix it so he can share his screen, I'm sure.
Believe I just did that.
Okay, your co-host.
Well,
Yep.
The guest.
I got it.
He needs to be a co-host to share his screen on it.
Oh, I got it. We're good. I'll just get it set up in a sec.
Okay, so he's now co-host.
Good. Can you guys hear me all okay?
Oh,
Yes.
Okay, now we see.
Click
Okay.
click that stop share at the top. Oh, yeah,
No, I think we got it now.
see the red button,
No, the top, middle.
the red button up there. in the-
Do you want to stop sharing?
No,
We want to stop sharing.
okay. All right. So it doesn't matter where I stand because I'm not going to be on. Okay, fine.
And then
Dr. Rob Zellup is an astrophysicist at NASA's Goddard Space Flight Center. His research focuses on the characterization of the atmospheres of exoplanets using both the transit and direct imaging methods. He's a member of the project science team for NASA's Nancy Grace Roman Space Telescope. And as you may remember, a few months ago, he did a presentation to us on the Nancy Grace Roman telescope. He's a member of the Roman Coronagraph Project Science Team, where he led the development of the science calibration plan. Project scientist and a lead for Exoplanet Watch, a citizen science project to observe transiting exoplanets to update their ephemerides to ensure the efficient use of large telescope time. He's the ground-based sub-working group co-lead for Pandora, whereby he's coordinating ground-based observations to support both the operations and scientific interpretation of Pandora data. The co-lead for NASA's Nexus for Exoplanet System Science and a science team member for the NASA's case contribution to ESA's aerial mission. And that wears me out. I mean, all the things he is doing. So, and Rob, I will tell you that we had a presentation earlier on planets formation in our own galaxy from one of our 6th grade members. So you have a high bar to meet after we heard about that planet formation. So we'll hear you talk about exoplanets. Thank you.
Yeah, I caught the end of that presentation. It was really awesome. Congratulations to whoever gave that talk. It was really, really great.
Okay.
All right. Thank you, friends. Can you hear me okay in the room?
hang on just a second. Yeah, we can hear you. We're trying to make you full screen, so we're seeing just your presentation.
You sure you really want to subject yourself to that? But that's okay. That's fine.
No, you're almost there.
Yeah, I can just get this video stuff go off. That's right.
Well, and the tricky part is we're not. Oh, yeah. Okay, so what do we? Oh, the upper right, the little, there's the box with the 3 boxes. Yeah, that. And which one do we want?
Probably,
Speaker? Yeah, side by side. Speaker, yeah, that second one. That second one, there you go. Yeah, and we're still seeing.
Yeah, you want me to?
Yeah, I'm not used to this laptop, so. Oh, okay. Yeah, then it's perfect. There we go. Yeah, that's better. We're still seeing a few little dots.
So you can shrink it space if you click that and drag it.
Hang on, Rob, we're just
There you go.
making it perfect.
That's
very cool.
Yeah, best we can get.
You can
Yeah.
pop him out, so if you right click that one.
And that'll be good to be able to see
I
him.
thought you could do that. Don't worry about it. Let's not.
What I was trying to do is get rid of all the little, the menu stuff,
Yeah,
but I guess there's not. What's that? Oh, well, it's better than it was.
Yes.
All right, well.
Yeah, all right. Cool, thanks, Jim.
Yeah.
All right, Rob, take it away.
All right. Well, thanks for having me again, folks. You had me about a year ago to talk about the Nancy Grace Roman Space Telescope, and you should know better than to invite me back. But despite your better judgment, you have. So thanks again for having me back. I'm talking about my Forte exoplanets, and thanks. I caught the tail end of that talk about planetary migration. It was a great talk. I learned a little bit myself. So thanks for giving that awesome talk. So I'm Rob. I'm an exoplanet scientist working at NASA's Goddard Space Flight Center out here in Maryland on the East Coast. And I love talking about exoplanets and love basically everything about astronomy. I was literally just watching about 45 minutes ago Star Wars: A New Hope. So I love Star Wars and I'm a giant nerd. So has me working at NASA. But yeah, lots of folks ask me, given that I love Star Wars and science fiction and space, if I ever wanted to be an astronaut. And the answer is definitely a hard no, because I'm definitely afraid of heights. There's actually young little Rob meeting his hero, the astronaut, at Kennedy Space Center, probably 35 years ago or so. So given that I'm afraid of heights, and that's kind of a prereq for working as an astronaut, what I think is the next best thing, I'm an exoplanet astronomer. So let's unpack what this means. An exoplanet is literally short for extrasolar planet, where extrasolar means anything beyond or outside of our own solar system. And then planet, you're all in an astronomy club. Hopefully you all know what a planet is. So therefore, an exoplanet is any planet outside of our own solar system. And I'm an astronomer, and you all hopefully know what that is as well. That's someone who stares at the sky, or more likely their computer for way too long. I don't do a ton of observing anymore. A lot of the observing is automated on my through computers. I have like a telescope array out in Los Angeles that's all fully automated through Nina. Definitely, if you haven't used Nina, definitely check it out. It's a great free automation tool. And that's kind of nice because I can sleep. But if I need to, or if I want to, I can also do some classical observing. But honestly, the most important tool in my sort of toolkit is my laptop. I'm on lots of meetings, do lots of work in coding, data analysis. So really, that's what a majority of my day-to-day is. And it's kind of nice because I can actually have a 9 to 5 instead of a 5 to 9. So as an exoplanet astronomer, I'm really, really interested in discovering planets outside of our solar system and figuring out what they're made out of. But what really drives me at the end of the day is answering that age-old question, are we alone in the universe? I think this is one of the most outstanding, one of the biggest questions we have left to answer as a species. And I'm really excited because within the next 10 to 15 years, I think we'll actually be able to answer that question. But before we start looking forward, let's take a look back and look a little bit about history. Despite exoplanets being one of the youngest fields in astronomy, it's been around since the mid-90s, honestly. There's actually a lot of precedence for it. Lots of folks have been thinking about it for the last few hundred, if not thousands of years. Giordano Bruno, for example, that 16th century philosopher up here, the Emperor Palpatine looking dude, he postulated that there are other solar systems out there that might have Earth-like planets on them, around them. Isaac Newton You're all aware that's the guy that gave us Fig Newtons, those delicious sandwich cookies. He said in his book Principia, where he talked about his theory of gravity, he said, and if the fixed stars are the centers of similar systems, they will all be constructed to a similar design. In other words, when we go out into the night sky, hopefully you have some clear skies somewhere near y'all. When you look up at the night sky, you see those stars up in the sky. And just like we have 8 planets around our own sun, 8, because we can all agree that Pluto is most definitely not a planet. When you go out in the night sky and you look up all those stars in the sky, it stands to reason that there's other planets around those stars as well. And we now know, hundreds of years later, that these 2 dead guys are absolutely correct. As our technology has gotten better, as we know where to look, how to look, as just things keep on improving, we have been discovering more and more exoplanets. And even this plot is out of date at this point. We actually now know of over 6,000 exoplanets to date. And thanks to missions like NASA's Kepler and TESS, which I'll talk a little bit about later, ground-based surveys as well, we now know that there's exoplanets pretty much everywhere, that planets are ubiquitous. So therefore, and Don, it's okay, you can be wrong. It is a dwarf planet, but it's not a planet, sorry. But there are at least as many planets as there are stars in the sky. So planets are everywhere. And if planets are everywhere, it might mean that there is life out there as well. So how do we find life? Well, we can break it down into this 3-step method. First, you have to find an exoplanet. Then you have to determine if it can support life. Then you actually have to find life on its surface. So let's look at various ways that we can use to find an exoplanet. Unfortunately, this is really difficult to do. And that's because stars are a pain in the butt, to use some scientific words. Stars are so much brighter than the planets that orbit around them. Even if we try to make things really, really simple, let's take like a really big planet, like a Jupiter-sized planet, and let's look at it maybe a few years after it formed. So it's still glowing in the night sky from residual heat from when it first formed. So we have a hot exojupiter. If we wanted to look at that hot exojupiter around a sun-like star, it's like looking for the light of a firefly around a lighthouse. But I'm observing it here from Maryland, and that lighthouse is off the coast of Los Angeles. So hot exojupiters are interesting scientifically. What I really want to do, and I really am excited to work on, is finding Earth-like planets around solar-type stars. Well, if we put that Earth-like planet or that sun-like star, that's like looking for the light of one bioluminescent alga around a lighthouse off of the coast of Los Angeles, and I'm out here in Maryland trying to observe it. These planets are millions, if not billions of times dimmer than their host stars. So we have to figure out a way of either inferring the planet is there or somehow removing the light of the host star to see the very, very dim planet shining through that. Luckily, there's actually a bunch of different ways that we can study exoplanets to date. But the 2 I'll be focusing on tonight are the transit and direct imaging method. These are both the methods that I have been lucky enough to specialize in graduate school and then as a postdoc and now as a NASA employee. The transit method has been used the most successfully to discover the most known planets to date. But arguably, the field is going towards direct imaging, where we can actually take photographs of exoplanets. So let's look at a little bit more in detail on the transit method. So if we're observing a star, we're really lucky that star will have a planet around it. And if we're even luckier, that planet will occasionally pass in front of its host star relative to our line of sight. And as the planet passes in front of the star, it blocks us from the star's light and causes the star to appear to dim. And this method is really powerful because this has been used to discover 4, if not 5,000 of the currently known 6,000 exoplanets. But this gives us the size of the planet. The bigger the planet, the more light it blocks out, the bigger the dip in light. Smaller the planet, smaller dip in brightness of the host star. And we can actually use this method to study a planet's atmosphere. When you're observing a star and a planet passes in front, the atmosphere of the planet will absorb some of the star's light at different wavelengths. And depending on how the planet absorbs light at each wavelength can tell you what molecules are present in that planet's atmosphere. I'll talk about this a little bit more later. So the transit method is extremely powerful because it's actually relatively cheap. I've seen, I actually have hundreds of people worldwide observing transiting exoplanets any given night with a telescope that's about 2.5 to 3 inches big. It's really, really small scopes. And it gives you the planet's size. But some disadvantages is that there's some biases with this method. We are biased towards finding large planets, bigger the planet, the bigger the signal, in short period orbits that orbit around their star relatively quickly. So it's easier to follow up that signal. And of course, you need that perfect geometry. If the planet's orbiting in this plane, it'll never pass in front of its star and never transit it and never block out its light. So the transit method is being leveraged right now by NASA's Transiting Exoplanet Survey Satellite, or TESS. This is a mission run out of NASA Goddard. This is a full sky survey that is aiming to discover 10,000 more exoplanets. So TESS will triple the number of exoplanets to date, more than double the number of exoplanets to date, which is pretty crazy. And TESS is really imperative for exoplanetary science because TESS will find the ideal targets, the things we want to then follow up. It'll find the easier things, relatively easier things, that we can then characterize with larger telescopes, such as the Hubble Space Telescope, which has observed about 50 to 60 planets. James Webb, I'll talk a little bit more about this later, is already observed, I think, about a few tens, if not over 100 exoplanets to date, and its very short operational life. And thanks to James Webb Space Telescope's giant primary mirror and its wavelength coverage, almost every single observation is completely changing the field. It's paradigm shifting. NASA's Pandora mission, which is a small set, and I'm repping the Pandora mission here with my t-shirt. That's a mission that I'm on the science team for that was launched in January of this year. And that's observing tens of planets to basically remove the polluting signal of an active star from the transit signal of the planet. So it's disentangling the stellar signal from the planetary signal. Ariel, which is a European Space Agency or ESA mission that I'm also on the science team for and has a NASA contribution for, they'll be launching at the end of this decade. And I'm really excited about Ariel because it will be fully dedicated to exoplanet atmospheric characterization. So while James Webb will hopefully observe tens, if not hundreds of exoplanets, Ariel will observe up to 1,000 of them. So Ariel will put the James Webb Space Telescope observations into a statistically significant basis. And one of the missions I'm really excited to be working on for the last year and a half or so is NASA's Habitable Worlds Observatory. I'm leading the charge on observing transiting exoplanets with HWO, and I'm really excited to use this instrument. It's primarily being used for direct imaging. I'll talk a little bit about later, but I'm going to really be pushing hard myself to use the transit method to characterize exoplanets and to potentially also search for signs of life. But if I want to observe a transit with any of these NASA astrophysics space telescopes, I have to know very precisely when those transits occur. So I have to really keep their transit timings fresh. I have to know very precisely when that will happen. So for example, let's say I want to observe my favorite transiting exoplanet, but it has a 15-minute uncertainty of when that transit will occur. Typically, people build in observing overhead to their observing scenarios, their campaigns with James Webb and Hubble. That's fine on a one-off, but if you start to observe tens or hundreds, if not thousands of planets, that cumulative time starts to add up very quickly, and you could waste hours, if not days of time, where you could be doing other impactful science. And about 1 hour of James Webb Space Telescope time is worth the equivalent of tens of thousands of dollars. So we're not using this space telescope as efficiently as possible to get the most bang for our buck, but also to do impactful science as well. But luckily, here's where small telescopes can help out, and you can help us out as well. This is why I started a project called Exoplanet Watch, which is a citizen science project to monitor transiting exoplanets. And what we have is people across the world, thousands of people across the world, helping us to observe these transiting exoplanets to update their times so we can more accurately predict when the next transit event will happen in the future. And by collaborating and participating in this project, you can directly help us enable NASA's science. So Exoplanet Watch is a collaborative effort meant to complement existing surveys such as the TFOP effort. All of our data is immediately public. We have no proprietary phase. So you could hop on our website once our results page gets back up and running, and you can grab any of our data or our data products and use it for your own research or studies. We have target requests by professional astronomers. We're actually waiting very patiently for Pandora to start its science operations, because as soon as it does, we're going to be simultaneously observing Pandora targets from the ground. And we're going to hopefully expand upon the wavelength coverage of Pandora, but also expand upon the temporal baseline by observing these targets before, during, and after the Pandora mission to get more science out of it as well. One thing I'm very proud of as well is that all of our observers are listed as co-authors. So if you do an observation and your observation is included for the first time in a published paper, we are asking those authors to include you as a co-author. If you do the work, you deserve the credit. And we've been very graciously funded by NASA's Universe Learning for the last few years. So as a citizen science project, we have both scientific goals, I talked about that before, to ensure the efficient use of large telescopes. We're actually now getting into the discovery and confirmation phase of new exoplanets. One of my undergraduate students at Arizona State University actually just discovered a multi-planet system that there was actually a press release about a few months ago, and that paper is getting published very soon. We're also helping out the Pandora mission by monitoring stellar variability, as well as larger flagship missions like Roman and Habitable Worlds. But as an exoplanet, so as a citizen science mission, we also have educational goals to engage and teach the public about exoplanets and enable them to do science. And really, at the end of the day, to help inspire the next generation of folks to pursue STEM fields and perhaps even become astronomers. And actually, as a result, we've had some high school students participate in Exoplanet Watch, publish their own papers, and now they go to places like Columbia and MIT and are studying astronomy, which is absolutely mind-blowing to me. So let's step through the user process. A little overwhelming, but I'll step you through each step. Let's say you have your own telescope. You can go to our website, you can use a plugin from the Swarthmore Transit Finder, and you can help observe any exoplanet any given night. We'll take data on anything that you absolutely want to contribute. And there are tens of targets any given night that we need your help observing. If you're like me and you live in cloudy central Maryland, or you don't live too close to Washington, D.C., and light pollution is not the best, you can also request data. We're about to relaunch our data checkout system in the next week or two, and you can go on our website and request data from one of our 10 telescopes. We have one telescope in Tucson, Arizona, the Micro Observatory, through our partners at Harvard Smithsonian right here. We also have an array of 9 telescopes outside of Los Angeles that have been observing as well. So we have hundreds, if not thousands, of data sets that we need your help to analyze. And you can fully participate in this project even if you don't have your own telescope. Then once you get your own data, either by taking your own observations or getting it through our checkout system, you analyze your own data. Lots of folks use Astro Image J. It's a very popular one. I know Dennis Conti, I think, talked to your club last year about it and probably gave you a really nice run through on it. There's also ExoWorld Spies or HOPS through ExoClock. And then we have our own code called Exotic that I'll talk about in a moment. But then once you analyze and reduce your data, you upload it to the American Association of Variable Star Observers. They're very kindly letting us use their website for free. And then you kind of sit back, relax, get published, or publish your own work from our own data. I mentioned Exotic. This is our exoplanet transit interpretation code. This is literally the same exact code that I use as a professional astronomer, but it's a little bit more user-friendly on the front end. But the back-end code is literally exactly the same. This can run on a Windows or a Mac or a Linux box, but it also runs fully online through the Google Colab Cloud. So you can actually run exotic and analyze data on your smartphone in as little as about 5 to 10 minutes. And this is how a majority of our users contribute data to Exoplanet Watch. They'll get data from a robotic telescope, either through us or through other means. They'll run it through Exotic, which will work on any telescope in the world. At least we haven't found one yet recently that has failed on. And then we'll produce scientifically motivated fits to data that you can literally just plop right into a published paper. And we've now had tens of papers written by folks that were not even NASA scientists that have used Exotic for their own studies and have published first author peer-reviewed papers, which is absolutely incredible. As I mentioned before, we are waiting with bated breath for NASA's Pandora mission. It was launched at the end of January this year, and they're undergoing commissioning right now. So they're making sure everything works and they know how to operate it and how to steer it and take photos. But soon, Pandora will be observing about 20 exoplanets for a day each and 10 times on repeat. And we are going to help out Pandora by basically expanding its science by providing additional observations in time, but also in wavelength coverage. And perhaps we will figure out a way to further help Pandora in its prime mission to disentangle that stellar signal from the small planetary signal as well. So if you're interested in joining Exoplanet Watch, you can get started here at this URL. You can scan this QR code. I'm really bad at remembering QR codes, so just Google NASA Exoplanet Watch or even Exoplanet Watch, and we should be the very first thing that pops right up. We'd absolutely love to have you. We have bi-weekly meetings. We're meeting next Friday. We're going to have a guest lecture about kilonova catchers, which is another awesome citizen science project. And yeah, basically these bi-weekly meetings are to answer any of your questions. I give guest lectures. We have guest speakers as well. And the community is absolutely incredible. Tons of amazingly nice people. Don't count yourself out from being able to do exoplanet transit observations. I am terrible about astrophotography, but even I can observe a transit. So you can definitely are capable of doing it, even from light polluted areas. We had a student from Pasadena, just outside of Los Angeles, that observed a transit with a 6-inch telescope with off the shelf materials, relatively cheap instrumentation as well. So hope to see you there. All right, I'm going to get off my high horse, off my soapbox right now. I'm going to move on to our regular scheduled programming. Let's now move on to how else we can find exoplanets. And that brings us to the direct imaging method. And just as you expected, the direct imaging method is literally taking photographs of exoplanets. We're not very inventive in astronomy, unfortunately. But as I talked about before, is an issue with trying to observe exoplanets. It's really hard to see the glint of the planet, whether that's reflected or emitted light, through the outstanding glare from its host star. But we can actually leverage technology that's been around for about 100 years. Hopefully, some of you were able to see the total solar eclipse. And during the total solar eclipse, when the moon passed in front of the sun, you could see the stars around the sun. You can also see the outer layers of the sun called the corona. Astronomers realized how important total solar eclipses were for studying the solar corona that they got impatient waiting for the next eclipse. They invented something called a coronagraph. And a coronagraph is basically something that simulates a solar eclipse. And now, 100 years later, we're using the same technology. But instead of using an eclipse on our own sun, we're using a coronagraph to simulate or to cause an eclipse of a distant star to help us to resolve the light of a nearby orbiting exoplanet. So let's look at how we can image exoplanets. Let me now try to share my audio. 1 second. Oh, nope, I can't. I'll just narrate it. No worries. Okay. So here's a cool video sort of explaining how we can directly image exoplanets. As I said before, it's really hard because they vastly outshine the light of their planets orbiting around them. But what we can do is we can leverage instrumentation and then advanced software post-processing to help us to block out the light of the star to resolve the planet orbiting around it. So if we look at the internals of a coronagraph, we have a little disk that blocks out the star's light, and then we have something called a mask that blocks out any light diffracted around that first little chronographic mask. Then what we can do is that cuts down a majority of the light from the host star, but we still don't see the planet there because there can be aberrations of starlight. On the ground, we use something called direct optics, adaptive optics, there we go, to use the secondary mirrors to help us remove the signals of the Earth's atmosphere. In space, we can actually also use adaptive optics as well, but instead of removing signals of the Earth's atmosphere, we can use that to further correct any aberrations of light in the manufacturing of the space telescope itself. So we can use adaptive optics in space sort of as like glasses to improve the vision of our space telescope. So these little mirrors are, these adaptive optics and deformable mirrors are very thin, and they quickly fluctuate to the ideal solution to remove that aberration of starlight to make everything look nice and crisp. And here you can start to see the light of the planet there. Then what we can do is it can sit on this and integrate it for a really long time, like tens, if not hundreds of hours, and apply post-processing to further pull out the signal of the planets orbiting around its star. And what's really, really cool about this method is it's been demonstrated on Earth using large ground-based telescopes, like the smallest I'm aware of is Palomar, the 5-meter Hale telescope. But we're about to do this for the first time ever with a space telescope. I'll talk about that in a moment. But we've been able to use direct imaging to look at extrasolar systems from the ground. So at the center, here's where your chronograph mask is. It's not absolutely perfect. Some light still scatters and diffracts around that chronograph mask, causing that speckle pattern of starlight here. But if you look closely, you can see these 4 little blips of light. And we're observing this over about 7 years. So these are 4 extrasolar planets orbiting around their star in real time. We're observing and making a movie here of an extrasolar solar system, which is absolutely mind-blowing. I could watch this all day, but I won't. Let's go on. All right, so now what? So we've discovered over actually 6,000 exoplanets to date. So discovering exoplanets is kind of passé. It's kind of boring now because we know that exoplanets are everywhere. And what the field is really moving more towards and has been doing for the last 10 or 20 years now is how do we take that next step from planet detection to planet characterization? How do we determine if a planet, for example, has an atmosphere? And if it does have an atmosphere, what molecules are present in its atmosphere? Does it have water? Does it have methane? Does it have the molecules necessary to support life like water? And just because a planet could support life doesn't guarantee that it does. So we have to take the last and most important step and the hardest step. We have to determine if that planet has life on its surface or not. Before we get ahead of ourselves, though, let's go to the next step in the search for life. Let's look at how we can determine if a planet could support life. So a metric that we usually use to help guide us to whittle down the 6,000 known planets into a handful of planets is to use something called the habitable zone. Now, if we were to look at our own solar system top down, we can look here and we see that Mercury and Venus are too close to the sun. They don't have liquid water on their surface and it boils off. Mars is a little bit too far away, it freezes out, but Earth is just right. It's not too close, not too far away, where liquid water can survive on its surface. And the reason we care so much about liquid water is because when we look at all life on the Earth, it requires liquid water to survive. So perhaps where we find water, liquid water, we would also find life. So that's a way to down select from the 6,000 planets that we know of to the few tens of planets. So this kind of tells us where to look. But then how do we take the next step to figure out what a planet actually has in its atmosphere? Well, we can actually leverage something called Beer's Law. So this is actually kind of complex, but luckily I found a really great explanation on the internet. So that is studying for a test or doing homework while beer is involved, making difficult classes such as physical chemistry more bearable. Great definition. I did this a lot in graduate school. Those of you who are underage, just tune this part of the talk out. But here's actually what real Beer's law is. What this basically does is this describes how a medium, like a gas, can absorb or reflect light. So let's make a thought experiment. Let's take a light bulb and put it on the other side of the box. And inside that box, let's pump it full of water vapor. Now, if we were to look at the light bulb through that box, we would expect that light bulb to look dimmer because the light is being absorbed and scattered by the water vapor inside that box. And actually, it behaves according to this equation. Relatively straightforward. The only thing that's unknown here is tau. And each molecule has its own unique tau absorption coefficient here. So by comparing what an object does look like, the light looks dimmer, comparing it to what it should look like, it should look bright, we can actually figure out what is causing that absorption here, that water vapors in the box. So let's look at an astronomy example. Let's pretend we're looking at a yellow star. Well, that yellow star emits yellow light. But if we put in between us and that star a nebula, for example, well, that nebula is going to absorb some of the star's light, and it's going to cause the star to look redder. Well, what we can do is then we can apply Beer's law, and we can figure out what that nebula is made out of. We can then observe what the object does look like. The star looks red. Compare it to what it should look like. It should look yellow. We can then use Beer's law to figure out that that cloud of gas and dust has molecules like hydrogen and helium in it. We apply this to an exoplanet. Let's say we look at an exoplanet that has like a hot super Jupiter, for example. That hot super Jupiter has a very hot core, just like our own Earth from when it formed. And that hot core is emitting heat and light. And as it goes through outer layers of the atmosphere that are relatively cooler, that light goes from red or white hot to comparatively red and cool. And then nerdy astronomers on the other side of their telescopes can use Beer's law to then figure out that that planet has methane in its atmosphere. Can also do it for reflection. In our own solar system, we have the sun. It emits its yellow light that hits the surface of Jupiter. Jupiter reflects that light, but it's reddened. And then nerdy astronomers on the other side say, hey, Jupiter has methane clouds in its atmosphere. So Beer's law is extremely powerful. It allows us to characterize any object's composition, such as an exoplanet, by observing how it emits, absorbs, and reflects light. So it can figure out what something is made out of without even having to travel there, just by how it interacts with light. So let's look at some real data. Here is some data of about 7 directly imaged exoplanets. This is data taken by one of the Gemini telescopes. And what we've done is we've taken these exoplanets and arranged them from relatively cool to relatively hot. And we've taken their light and we've passed it through a prism to change that white light into a rainbow of colors to see all the different colors here. So we've taken that light and stretched it out and plotted it versus its wavelength. And Beer's law is really powerful because if we look at how a planet's light varies with wavelength, we can actually figure out what molecules are in an atmosphere of an exoplanet. So for example, if I see a bump and wiggle at these wavelengths, this is where water most strongly absorbs and emits light in infrared wavelengths. So if I see a bump or wiggle at these wavelengths, that planet potentially has water in its atmosphere. If I see a bump or wiggle or signatures at these wavelengths, I can infer that that planet has methane in its atmosphere. So just by using Beer's law, we can look at the rainbow of colors of our exoplanets and then figure out what molecules are present in their atmospheres. Now, some of you might have noticed these lovely gaps in the data. I did mention this is data from one of the Gemini telescopes here on Earth. That's unfortunately where the Earth gets in the way. That's because our own stupid Earth has the same molecules in its atmosphere that we want to observe in these exoplanets. It's a lot like trying to look through a picket fence and be a creeper into your neighbor's yard. In order to really be able to fully get the information to unlock these additional wavelengths of light, well, we can do two options. We can either build our telescope on a much higher observatory, such as the top of Mauna Kea. We could fly it on an airplane or a balloon, or we can fly it out into space. And this is why it's so critical that we have things like the Hubble Space Telescope and the James Webb Space Telescope, because these two telescopes are above the Earth's atmosphere. They don't have to look through the Earth's atmosphere, and they can access all those infrared portions of the spectrum of these exoplanets to characterize their compositions. So here's actually some real James Webb Space Telescope data. James Webb is 6.5 meters, Hubble's 2.4 meters. So James Webb is at least a factor of 2 to 3 the larger in its radius and diameter. So a factor of 4 to 9 larger in its total collecting area. But what James Webb also has is extended wavelength coverage. So James Webb has enabled us to access wavelengths of light that we've never had the opportunity to observe before from the ground, or the Hubble Space Telescope or other missions. And this is critical because this gives us access to new molecules such as sulfur dioxide. We can also look more easily for things like signs of methane out here as well. For comparison, here's where the Hubble Space Telescope typically observed. So James Webb gives us two things: a giant mirror to collect as many particles of light as we can, but it also enables us to expand on its wavelength coverage from the Hubble Space Telescope and access new molecules for the first time ever. And we just had James Webb launch December 25th of 2021, Christmas Day. So now, just over 5 years later, a little over 5 years later, it's been doing impactful science. Well, what's really, really cool is the next NASA flagship mission is to be launching this fall in early September. That's the Nancy Grace Roman Space Telescope. This is the same size as Hubble, but it has 1 to 200 times the field of view. So Roman can actually do Hubble quality science over 1,000 times faster. But what I'm really excited about it is that it has an instrument on board that will enable us to do direct imaging using adaptive optics for the first time in space. I'll talk about this in a second, but before I do, let me quickly give you a rundown on why it's called the Roman Space Telescope. That's because it's named after Nancy Grace Roman. She's NASA's first chief of astronomy. She's also the first female executive at NASA, and she's sometimes called the mother of the Hubble Space Telescope because thanks to Dr. Roman's activism, she was able to convince folks that spending millions of dollars on a space telescope was worth the investment. So in her honor, they have named the Roman Space Telescope after her. And one of the instruments that Roman has on board that I'm extremely excited about is this coronagraph. So with large ground-based telescopes, we are really limited to looking at big, bright planets very far away from their host stars. Roman will enable us to look at planets that are more temperate, that are cooler, that are dimmer, and also closer to their host stars. So for some of the first time ever, we'll be able to image Jupiter-like planets. And that's really extremely exciting because we'll be demonstrating the technology that's worked so well on the ground for the first time ever in space. And we'll be learning lots of lessons of, what sort of technology to use, what sort of hardware, lessons learned, post-processing methods, what to do, what not to do. And all those lessons will be applying to NASA's next generation mission called the Habitable Worlds Observatory. I'll talk a little bit more about this a little bit later, but this is NASA's next flagship mission launching in about 10, 15 years or so. And that's being explicitly designed to image Earth-like planets around sun-like stars, but more excitingly, to look for signs of life and to determine if there's life out there in the universe. So let's talk about how we can actually find life once we've determined that a planet, through Beer's law, could support life in its atmosphere or on its surface. So step 3, let's find some life. This is actually a really hard thing to answer. And this is a really big question in astronomy and astrobiology. It's what are the bumps and wiggles of a planet's spectrum? What are the signals that indicate that life exists on the surface of that planet? Luckily, back during the days of the space race in the 50s and 60s and also the 70s, scientists, when they sent missions out to the solar system, they also pointed them back at the Earth to image the Earth and basically try to figure out what made it so special. They analyzed the Earth's reflected and emitted light, and they could see evidence of oxygen, such as produced by plants and algae. They could look for liquid water on the surface. They could also see other biological activity as well, such as cows. Cows actually, through their egregious farts, apparently make tons of methane out there. The problem is you have to rule out all explanations because a lot of these molecules also occur abiotically without life. So you have to figure out in concert, you have to look at the whole picture to determine if that planet has life on its surface or if those signals occur naturally. But luckily, this is the question that HWO is going to answer. This is NASA's next flagship mission, launching in about 10 to 15 years. It's going to be at least as big as the James Webb Space Telescope, and it'll be covering the ultraviolet, the optical, and the near infrared. And what I'm really excited about is seeing images like this. This is actually a simulation from the Habitable Worlds Observatory, observing our own solar system. If it was about, I believe this is about 5 light years away. So here you can see there's Venus, there's Earth, there's Jupiter, there's Saturn. So you can actually directly see planets orbiting around their star. What makes this even more compelling is we can actually look at the rainbow of light of these planets to then characterize their compositions and look for those bumps and wiggles that tell us that light's there. We can look for global biosignatures to look for global biospheres. We can look for ozone and water and carbon dioxide, and all together we can determine to some degree of certainty if that planet has life on its surface. But wait, there's more. Habitable Worlds will not only look for Earth-like planets and signs of life, but the requirements that we need, a giant telescope in a very stable orbit with very stable seeing and precision, that will enable a ton of other really paradigm shifting science. We're actually going to be using it for planetary science as well to help us study near-Earth asteroids, to help us look at ocean worlds such as Europa and Celadus. We're going to use the ultraviolet to look into the cores of active galactic nuclei of active galaxies to determine how they work and how they're formed. And we're going to be looking and studying black holes, dark matter, dark energy. HWO, despite its name, will not just do exoplanets, it'll change the entire field of astronomy from the UV to the near infrared. So again, it's at least as large as James Webb. It has that coronagraph that'll enable it to do direct imaging. The instrument that I'm working on is the high resolution imager or instrument. We're going to be using that for planetary science. I'll be using this as well to do transiting exoplanet science, to look at these signals and maybe discover life as well. And then other folks will be using it for the UV multi-object spectrograph to look at things like active galactic nuclei to peer into the core of these galaxies to understand better their formation and structure. Okay, so where are we now? Unfortunately, despite what the History Channel and Ancient Aliens might tell you, we have yet to make any conclusive detection of extraterrestrial life. And maybe it's just because we're all alone. Or maybe we just haven't found them yet. Honestly, I think that our technology hasn't met that sort of level where we have the sensitivity to find it. Jill Tarter, she is the SETI scientist who is the inspiration for Carl Sagan's book and then the movie Contact. He had a really great analogy. If we were to shrink the entire universe into the size of the Earth's oceans, we've still really only explored the equivalent of one glass of water's worth. So despite all the things we think we discover and understand, there's still a lot out there to do. But luckily, we're in this golden age, in my opinion, of exoplanet science. And we've been sort of standing on the shoulders of giants and building up and learning what to do, what not to do, what methods to use, what instrumentation to employ, what software to leverage. And that'll be building up to the Habitable Worlds Observatory that I think when it launches about 10 to 15 years from now, it'll have that capability to finally answer that age-old question, are we alone in the universe? So with that, thanks for your patience, thanks for sticking it through, and I'm happy to take any questions you might have.
Questions, anyone?
How long do we?
I have a lot.
How long do we have the Webb telescope?
So Webb, luckily, it had an operational lifetime that they aimed for about 10 years. But luckily, its fuel was used so efficiently that it's expected to last now up to 20 years. So lots of more time left on Webb, which is awesome.
Can you hear me?
Yes.
So Beer's law sounds a lot like spectroscopy, which we use at work, and there's overlap that we find. Like, titanium has a signal that overlaps with silicon in places. Do you have overlap in your Beer's law data? So, water could also be something else.
Yeah. So Beer's law enables us to interpret the signal of light as a functional wavelength. So we can use it for photometry. We can also use it for spectroscopy. So in this figure right here, if you look closely, water band here overlaps with the methane band. So what we'll do is we'll tune our data and our observations to try to pick out where those bands don't necessarily overlap. So right here is actually a very strong water band between 1.4 and 1.6 microns, where water is almost the only molecule that absorbs. Unfortunately, that's also where the Earth's atmosphere gets in the way. So that's why Hubble has been so crucial, is it's been able to actually pinpoint that wavelength range and look for that water signature. That's why I'm so excited about James Webb, is because it's been able to give us access to those other wavelengths of light where other molecules don't overlap as much. This plot goes out to about 5 microns, but right here is 3.3 microns. There's actually a really good methane band. I don't know why it's not labeled on this plot. So yes, molecules can overlap. That can confound your interpretation of the atmosphere of the planet. Luckily, a lot of molecules do have their own unique spectral signature. So water looks very different at 1.4 microns versus methane at 3.2 or 3.3 microns. But what you also have to do is sometimes you have to leverage physics and what we think the atmosphere is doing to further interpret the planet's atmosphere to figure out what molecules are in it as well. So it can get a little confusing, admittedly, especially in Hubble data alone. James Webb is helping us break that degeneracy through its high signal to noise. Awesome question. Thank you.
Yes, go ahead, ask a question.
I have a question. So,
Yeah.
how does direct imaging compare to radial velocity? Like, is it better or worse?
Different. They're just different methods. Yeah. So the radial velocity method, for folks who don't know, it's looking at the Doppler shift of a star based on the planet tugging on it gravitationally. So what you'll look at is you'll look at the spectral lines of the star, and as the star comes towards you, because the planet gravitationally tugs the star towards you, the spectrum of the star becomes blue shifted. And as the star goes away from you, the stellar spectrum is red shifted. So by looking at this radial velocity shift, blue shift and red shift, and that periodic motion, we can back out that one of planets there. We can also, though, measure the mass, the size, the weight of the planet. Because the bigger the mass of the planet, the more Doppler shift it'll induce on its host star. The direct imaging method, though, enables us to take these very cool photographs, and grab one right here. 1 second. Shoop, shoop, shoop. Enables us to actually take images. So radial velocity is an indirect method. We never typically observe the light of the planet. We infer the planet is there. Direct imaging is powerful because it allows us to see the light emitted or reflected by the planet's surface. And this doesn't really require as much that geometry. Radial velocity means the star to be coming towards you or away from you. Direct imaging is not as sensitive to that geometry. So we can almost observe the planet at any given time in its orbit, where radial velocity needs that special orbit. So this is why we are moving towards direct imaging for looking at Earth-like planets. One of the many reasons. Another reason is that stars are active, and their activity, even just granules on the surface of these stars, can actually overwhelm the planetary signal. They're actually unable to see anything smaller than an Earth-sized planet around a solar-like star because the stars are effectively polluting the signal and getting in the way. Excellent question. Hopefully I answered that for you.
So
I don't mind, I guess. Okay, we had a question, there's a question in the back.
Yes, is there any way to look for like exoplanetary moons and whether any of those could be?
Did you hear
So
that?
it was a little hard to hear, but it was about exoplanetary winds.
Moons.
Moons, exomoons, yeah. So this is something that folks like David Kepping, a university professor at Columbia, are really excited in trying to do. Unfortunately, exomoons are very, very small compared to their host planet, so the signal is very small as well. Folks have been leveraging typically the transit method to look for exomoons, and to date, there's been some tentative detections with both Hubble and James Webb, but as far as I'm aware, there's no conclusive detection of exomoons. I just really think that our technology isn't sensitive enough to exomoons quite yet, but they should be out there. I mean, if you look at our own solar system, Earth has a moon, Mars has a few, Jupiter and Saturn each have tens of moons on them, around them. So they're probably out there. We just don't have the capability, the sensitivity to observe them just yet.
on that note, I recall Bernard's star being the closest, most like our star. If not, there is one somewhere around there. If an Earth-like planet was in an Earth-like orbit around a star fairly close by, how close are we to being able to find that?
Oh, HWO should be doing that. So HWO is going to be looking at the closest stars, the brightest stars, the highest signal to noise, to look around them to block out their host star's light, and to then discover Earth-like planets orbiting around them. So potentially HWO, when it launches, typically from the stage we're in a very early stage of the mission. We're still defining it and designing it. From where we are to where we launch is about 10 to 15 years typically. But once HWO does that, it should be able to look at planets, look for planets around those bright nearby stars for sure.
Right in the back.
Yeah, could you find life on a moon or only a planet?
Yeah, and that's actually a great question. That actually expands potentially our view of habitability. So, if you remember the habitable zone, that is taking into account the distance of a planet around its host star. And if a planet is too close to a star, it's too hot. And if it's too far away, it's too cold. But things like the Earth are on the right distance where liquid water can survive. There have been studies about smaller habitable zones on moons around planets. So, for example, Europa has an icy crust. It kind of looks like the planet Hoth. Yes, I'm about to watch The Empire Strikes Back in case you can't notice. But under that icy crust is actually a very big salty ocean. And that's because when Europa orbits around Jupiter, Jupiter's gravity tugs at Europa's surface and actually causes it to bend. And that friction causes heat, which causes it to have these massive oceans under its surface. So this is something that NASA's Europa Clipper, which was launched a few years ago and will be getting at Jupiter the next, I think, 4 years. It's going to start investigating Europa to look potentially at its plumes to see if you could start to maybe pick out some organics, potentially signs of life. And we'll be observing Europa and Enceladus as well with HWO. But perhaps a future NASA mission that will land on Europa's surface will dig under the ice and then look for signs of life. So yes, life could potentially exist on forest moons of Endor or Europa or Enceladus. But what we do is we only see life on Earth in our solar system. So we apply that very human-centric view to, to the rest of the universe. So it's in a sense limiting, but we need to down select from the thousands of planets we know today to a few tens that we can then follow up in details. And I think I saw Angelo had his hand raised online as well. Did you still have a question,
Yeah,
Angelo?
I had a similar question to what I think you just answered. The fact that there's so many more exoplanets that are not in the habitable zone as compared to the ones that are. Could we be looking for the wrong signatures in the wrong places?
Oh, yeah, for sure. And we are applying a very biased view of the universe. When we look at our own solar system, We only find life on Earth. So we're applying that bias and we're looking for Earth-like planets out there. There could be other forms of life that exist elsewhere in extreme environments, like extremophiles, like tardigrades or water bears. But we haven't found anything yet, any life that exists without liquid water. So that's what's driving us right now. That's why NASA is so passionate about following the water, for example, on Mars, is that where we find water, we might also find life. But we could be wrong, which could also be pretty cool.
Okay, thank you.
Yeah, great question.
Yeah.
Of the 6,000 known planets, how many have water and are in the habitable zone? What percentage?
So, yeah, a few tens of them are in their star's potential habitable zone, but a lot of planets have water in their atmosphere. We think that almost every planet should have water in its atmosphere, and that's simply because water is one of the most abundant molecules in the universe. It's just hydrogen and oxygen. But that doesn't guarantee that life is in their atmosphere or on their surface, because a lot of these planets we're finding today are too close to their star for life to survive. They're like thousands of degrees, so they're way too hot. And I'm seeing in the chat, someone's asking about looking for carbon-based life forms as an assumption we've made. We obviously don't know anything else, but could that be? And yeah, we are definitely applying a human-centric biased view of the universe. We think life will be carbon-based because it's a nice stable molecule that allows really nice reactions that are supportive to life. But maybe there's other non-carbon based life forms out there, or life that doesn't need water at all. Some of you might have seen the documentary Project Hail Mary. You know, there could be some weird extreme life that we haven't considered out there that's just waiting for us to discover.
Anyone else here in the room or online? Okay, well, let's thank Rob once again for a great talk.
And thanks again for having me, folks. Really appreciate it. And have some delicious Texas barbecue for me. I missed that out here in Maryland.
Okay, thanks. Bye-bye.
Bye, everyone.
Thank you.
Okay, anything else anybody needs to say? Okay, well, some people do go over to Crown and Anchor, which is over on San Jacinto afterwards for food and drink. So anybody wants to go over there, there will probably be some people there anyway. So okay. Thank you for coming. Good night. Yeah.